Video is about finding k closest points to origin, and the problem statement says that we have two inputs, we have array and we have k. So let's say we have an array where every element is actually a pair of x and y coordinates. So we have 1 and 3, x is 1, y is 3, then we have -2 and 2, then we have 5 and 8, and then we have, let's say, 0 and 1. We have k is equals to 2. Let me just write it there. So we have k is equals to 2, and you need to find two closest points to origin. So what would you do is you actually find distance based on x square plus y square, how you just simply do in maths, and then you are going to compare the distances to see which one is closest. So for your 1 and 3, you have a distance of 3.1. For your -2 and 2, we have a distance of 2.8. Then for 5 and 8, pair of coordinate, we have a distance of 9.4, and then for 0 and 1, we have a distance of 1. So which one is closest? Clearly it's this one, and then it's this one, which brings us to a conclusion that 0 and 1 and -2 and 2 are the two pair of coordinates which are closest to origin, because origin is 0, 0. And these are the distances which were calculated. So that's very clear how you're actually going to capture this problem. And of course, k is always going to be a valid value of positive integer. That is something that we can safely assume. So let's stop for a moment over here and see if we can recognize the pattern so far. So we do see we have to find k closest. That's one signal. The second signal is we need k specific points, and we do not need all the points. And these two signals kind of hint us that this problem might be a top k problem pattern recognition. And if you have watched my video around kth largest element, this one might seem familiar. Let's talk about our solutions, and I'll start with the naive solution now. So what can be the naive solution? The naive solution is simply that you have your different elements that we have here. So I'm just going to copy them. So we have 1 and 3, the distance is 3.16. Then we have -2 and 2, the distance was 2.83. Then we have 5 and 8, the distance was 9.43, and then we have 0 and 1, and the distance was 1. So we traversed through this array and we try to find out distances, and then you sort these distances. So we have 1, 2.83, then we have 3.16, and we have 9.43. So we sort it, and then we just simply pick k elements. So if k was 2, I just need to pick the first 2 elements. If we talk about time complexity and if we talk about space complexity, we know that it's the sorting part which is taking most of the time, which is n log n, and space complexity is constant, big O of 1. And it is big O of 1, let's suppose, because our sorting algorithm was in place sorting algorithm. Again, I'm not going into the details of sorting itself. I'm just trying to compare it, and I'm assuming that you are someone who already does have a know-how of how sorting and searching algorithms they work, particularly how sorting algorithms work when we're talking about this particular problem, and what are the data structures that exist, what are the time complexities, what are the space complexities. So that's already a prereq for this video. And let's see now that how we can tweak the time complexity. The problem is that let's suppose you have n as 1 million elements, and then you have, let's suppose, k is equals to 10. So we are actually sorting all these 1 million items or elements just to find our 10 closest points. And that is where the bottleneck is. Whereas we actually need to just keep track of k closest points, and let's say if we can kind of have a boundary within those k closest points. I'll clearly let you know what boundary means, but I'm just trying to build a motivation here. And if we can have a boundary within those k closest points that can serve as farthest of the closest. So just keep this context in mind, and let's see if we can use a maximum heap, because we need the concept of boundary and how that can be used to solve this problem. So we have our points as 1 and 3, minus 2 and 2. We have as 5 and 8, 0 and 1. I have just copied these points right now over here. And then we knew that our distances were 3.16. For minus 2 and 2, our distances were 2.83. And then we have 9.43, and this is 0 and 1. No, we had a distance of 1 over here. So up till now, there's nothing fancy. We just have points, and we have just traversed the area, and we have just calculated distances. As simple as that. And our k is 2. And I'm going to try in this process with maximum heap, because I need a boundary at the root node as something which is farthest of the closest points. And we are just going to keep maximum heap with elements, with number of elements equal to k. And let's see how that can solve our problem. So right now, let's see what is the heap state. It's right now empty. We have an incoming element of 1 and 3 having a distance of 3.16. So my size is empty, it's 0. 0 is less than my current size of my maximum size, not the current size. So the maximum size is 2. So right now my size is 0, and 0 is less than 2. So I can just push 1 and 3. So my heap would have 3.16 at its root node. I'm not writing pair of coordinates as well when I'm drawing heap, just to keep it a little simple. But you can look into the technical details for that when it comes to coding. And then we have another pair which is 2.83, and now my heap size is 1 since I have pushed just one element. So 1 is still less than 2, which is k over here. So I'm just going to push it, and since it's a maximum heap, so I have 3.16 at the top still, and I have my 2.83. And now my size is 2 after this. So size was here 1. Let me just write it, and now the size is 2, which is equal to 2. And now I have another incoming element. So I have processed this one, I have processed this one, and now I am here. So now 5 and 8 is incoming with a value of 9.43. Now I want you to just think for a while that what is the purpose of heap. So the purpose of heap is we actually have only k elements in heap, which are the closest ones. So this 3.16 is actually like a boundary. This is a maximum heap, and I wanted to go for a maximum heap because we need to have some kind of boundary or a guard to see that, hey, which one is the maximum element so far. So you have 9.43, and you would say, is 9.43 greater than 3.16? And you are comparing at this particular point because the size of heap, which is 2, is already equal to k. So you compare it and you say that yes, this is true. You make this comparison call, and then you pop the maximum boundary that existed up till now, and that boundary existed up till now till here with the value of 3.16. So I'm going to pop 3.16 because now that is not the maximum value, and I'm going to push 9.43 as well. So my heap is now just going to look like this: 9.43 at the root and 2.83 as child. Now this part has been done, and now I'm moving towards the last part of 0 and 1. I have a distance of 1, and my size of the heap current is 2, which is equal to 2. So size is 2, which is equal to 2k. So I'm going to make comparison call again. I can't just push it blindly. I need to see whether I have to make a pop operation or not before pushing. And even either a pop or push operation is needed or not. So I just compare one. Is it greater than the maximum or the farthest point that we have currently in our heap? So is 1 greater than 9.43? That is false, so I'm not going to do anything. I'm just going to keep my heap as it is. So if you see at every point, this root node of the heap was actually the farthest of the closest points of origin, and that acted as a guard in order to see that whether I need to make a push operation or a pop operation or not. So that is the reason why we needed a maximum heap to solve this problem. So I'm just going to talk about the time complexity and the space complexity that we have right now. So the time complexity is n log of k. Why is it n log of k? Because every pop and push operation takes log k. At worst, we might have to push and pop at every incoming element from array, every element from array, and that's the reason it's going to be n log of k. And space complexity is going to be big O of log of k. Why? Because we are never ever exceeding k. We are making sure that we are just using this maximum heap to actually keep track of k elements at maximum. So yes, that's a trade-off as compared to sorting, where we just had constant space complexity. And let's just take an example here. So if we have n log of k, that would mean, let's suppose if n was 4, that would mean 4 log of 2. So we had like 4 operations when we used maximum heap, in comparison to n log of n for the sorting one that we saw earlier, where if n was 4, then we had 4 log of 4, which was actually 8 operations. So you see that when you tweak it down from n log n to n log k, you roughly have half the operation, which means 2x faster. So let's also try to see, if you have n is equals to 1 million, how much operations would actually differ. So with n log n, let's suppose if you have n is equals to 1 million and if you have k is equals to 10, so with n log n when it was with sorting, and it was n log k with maximum heap, so with n log of n we would have around 20 million operations, and with n log of k we just have 3.3 million operations, and that's a huge difference, which is like around 6x faster. And if we talk about memory, with sorting you would have 1 million points all taking your memory, whereas with maximum heap it's just 10 points. I mean, the difference is insanely huge. So that's it, how you can actually use a heap to sort out this problem. This is actually the second problem where we have used a heap of size k. The first time we actually came across this pattern was in my another video where I was trying to find out kth largest element. It was also a heap, but that was a minimum heap of size k. And today, the problem that we just saw, it was around k closest or k smallest points, and it was actually maximum heap of size k instead of minimum heap. And maximum heap, because I explained in the video already that we need some kind of guard at the root node to see which one is farthest from these closest ones. So it was just a maximum heap of size k instead of having minimum size of k, which we saw in the previous video. And which brings us to a conclusion that these are just different problems, but they are using the same core approach. And that's it for the video. In the next video, we'll look at another problem and let's see if our pattern continues. See you there.